Okay. So some explanations, just a sec. Again, I'll try to explain the idea behind the quiz, okay, and how we're going to grade it. So there are 3 quizzes throughout the year, right? This is number 1. You have 2 more set in your itinerary, like the schedule throughout the year. Each quiz will contain 5 questions. Overall, you get 15 questions. Okay? Now, the quizzes are worth 10% out of your grade. This means that if you answer 10 out of the overall 15 questions, okay, you'll get the full 10%. Anything more than that is bonus points. Okay, so the point is that the quizzes are here to help you. Okay, last year the test was 85% of the grade. There were no quizzes, and people asked us, please give us quizzes so we can prepare ourselves throughout the week. Okay? Actually begged us. So the whole point is that if you get, let's say you get 3 questions correct this time, and then you get 4 questions correct next time, and then you get another 3 questions correct next time, you get full grades on the quizzes. Okay? So you don't, it's not a pass-fail system, it's just counting the number of questions you answer correctly. Is it clear now?
How many minutes do we have?
You're going to have about 25 minutes for the quiz. It's 5 short questions. I'm sure that most of you will be able to leave in like 10 minutes, and then you'll get free time. It's all multiple choice.
Wait, maybe said maybe I made it just as well. Is it for the one who needs to have all the answers correct in order to get the point? No.
Okay. Okay. So, how many of you feel anxious about the quiz? Okay, that's healthy. I can promise you that this system is meant to work in your favor. Okay? I know it's stressful, but it is for you. And this is in comparison to last year's, few years, and the people asked. Yes?
I find that the wording sometimes is a little bit tricky and hard to understand. That sometimes, like, I don't know, semantically, there are certain words that are chosen within the questions that have an alternative meaning when you understand English very well. And I find that to be like very challenging if you're incredibly critical of the questions.
Yeah. So it's always true, especially in Israel, that where the TAs and me are not a native English speaker. Okay, so we might always have these kind of problems. Alert us to these problems. We never want to cause you to fail. We want you to have all good grades. Okay, that's really our purpose. The grading system for the test, for example, we have a positive curve up to 76. I want this class to get an average of a 9. Really, I want you guys to surpass all the previous classes by far. Okay, we do want you to get the best grade. And if there is a question that has a double meaning in it, either we'll fix it or we'll just give 4 points. Yeah.
So just to follow up, you said to alert you about the English.
Yeah.
I think in the second question of the homework where it said in case.
Oh yeah,
So a lot of people didn't like the question, but I think.
Okay, someone sent me an email about that. Okay, or the TAs. We'll try to fix it. I don't remember, it's not important right now. Okay, let's get going in today's recitation. Okay, we have about an hour before we start the quiz. So let's get as much as we can. Now, we're continuing today with the semi-revision that we're doing these past 2 lessons. Okay, why is it a semi-revision? Because we are going over previous materials, but we're also trying to reinterpret them, right? To give them a fuller, more theoretical meaning that will give us the basis that we need for this course. So today is another, like this kind of semi-revision about the different statistical tests. So we're going to go over Z-test and T-test, which I know that you know, we're just going to give them some extra meaning. Okay, so empirical research has an enemy. Okay? The enemy of empirical research is chance. Okay, I stole this from my professor of statistics in Philadelphia. So we're combating chance. What's chance? Chance means that something occurs in random. Okay? That the world is random, that nothing has any structure or rules to it. And if something is random, then you can have all different kind of results. Now, I'm going to enhance this meaning. It's not that chance is just something that is completely random. It's also something that we don't understand. Okay? If I measure the effect of coffee, okay, on sleepiness, and for example, some people will come into the experiment after a good night's sleep, and some people will come to the experiment after a bad night's sleep. This is something I did not control for. Okay, I did not measure their hours of sleep. So this will also go into chance. Now it might not be chance at all, but I didn't measure it. Okay, so I can't consider it as something systematic. So we're combating chance. Okay? And in general, all our statistical tests, we want our results to reflect a real result. Okay? I told you that we're trying to describe something real, an abstract rule. Coffee makes you less sleepy. That's an abstract rule that is not it's not supposed to be for a particular group. Right? We're taking a sample, we're trying to conclude about a population, about the abstract. So we want our sample to reflect a real result. But there's always a chance that it was caused just by chance, okay? Just by randomness. Okay, I can have the most extreme result, and still it could have been caused by chance. So that's what we always try to figure out. Are our results real, or are they caused by chance, or might they be caused by chance? Okay, any questions on this slide? So the most common question that we go into in statistics, that we study, is a comparison between groups. We have one group, we have another group, and ANOVA will have 3 or more groups, okay? And we want to compare between them. So coffee versus no coffee, men versus women, NBA players versus general population. We always make this comparison. Now, if you notice, we always phrase our questions in a very simple manner. Are NBA players taller than the general population? Okay, we're not asking how tall are NBA players relative to the general population. No, we're asking a yes/no question. Okay? Is there a difference, or is there no difference? Okay. So what we measure in our sample is a difference, right? We measure this difference between the coffee, no coffee men, women, and NBA players. We measure a difference, and we want this difference to reflect something real. But then we also measure what is the difference that we should expect by chance. Okay? A difference by itself will not tell us anything. The number by itself will not tell us anything. So, for example, I'm going to measure Martians, okay? Martian men and Martian women. And I'm telling you that in my sample, the difference between Martian men and Martian women in height is 1 meter. Okay? In my sample. 30 Martian men, 30 Martian women, I found a difference of 1 meter. Is that a lot? We need to answer this question, is this a big difference? We need to compare it to what we should expect by chance. Because if Martians go from 1 meter to 42 meters, a difference of 1 meter might be very small. Okay? If there's a large variability, the difference it's seen as large can actually be very small. So we measure the difference obtained between the groups of interest, we measure the difference we can expect by chance, and then we compare them. Okay? And we ask, is the obtained difference larger than the difference that is expected by chance? We compare the two measures and we calculate a statistic, right? The Z statistic, the T statistic, and the F statistic, which we'll get to in the next lesson, are all this formula, this simple formula. Difference between the groups versus what is the difference we should expect by chance. So if we have a large statistic, it means that the obtained difference is much larger than what we should expect by chance. Isn't it? The larger the difference, the less likely that the obtained difference is a result of chance. Is this idea clear? Okay, good. So to make a conclusion about the population, we compare the statistic to what we consider unlikely to occur by chance. So that's the critical value. Okay, so the critical value, we choose a critical value to represent, okay, assuming that the null hypothesis is correct, because we always assume the null hypothesis is correct, this will represent an unlikely result. It is possible, right, to find a very large t-value. Just by chance, H0 is correct, but just by chance we found a large difference. So we want this statistic to be more extreme, usually larger, but more extreme than this value. So if it is more extreme, then we say, okay, so this obtained difference is significantly larger than what we should expect by chance. Okay, moving on. Here's the running example of the day. A group of 4 researchers want to examine whether artists drink more alcohol. Okay. Each researcher conducted a separate study and used a different statistical test to examine their hypotheses. So the first one. Let's start, this one will move very fast and then we'll make it slower as we progress. So the first example would be this one sample z-test. The Australian researcher wanted to examine whether artists drink more or less than the general population in Australia. More or less, so it's a two-sided hypothesis. We're not expecting a larger value, we're not expecting a lower value. She sampled 100 Australian artists and measured how many liters of alcohol they drank in a year. She compared the average score to the known average in the population. So, classical z-test, we have one sample. Okay. This is the average score, n equals 12. The general population in Australia drinks 10 liters of alcohol a year. It's not 10 liters of beer, it's 10 liters of alcohol. Okay? And this is an actual value from the, okay? Australians drink a lot. So we have the general population, and we have the artists. Now we see that the obtained difference is 2. Is 2 a lot? Is 2 a small value? The only way we can know is if we find what we can expect by chance. Exactly. And this, in a z-test, is very easy to get the difference expected by chance because it's based on a known value. In a z-test, we know, that's a very unlikely occurrence, but in a z-test, we know the variance and the standard deviation in the population. That's this small sigma. So sigma is the average difference we expect by chance in the population. Based on this sigma, we can calculate the standard error. Now, I remind you, the standard error is the same as saying the standard deviation of the sampling distribution, right? The sampling distribution, this tool that we're going to build in order to check our hypothesis. So the standard error is the standard deviation of the sampling distribution. So we get this sigma, and to get the standard error, we simply divide by the square root of n. So if sigma is 10, it says that we can expect an average of 10 liters in the population. Okay, an average difference. So sigma is 10, we can expect a large variability in the population. The average is 10 liters, but it means that some people will bring 20 liters, some people bring 30 liters, some people will not bring it all. But the standard error, if we take a sample of 100, I forgot to mention it, she took a sample of 100, okay, to make it easier. So if we take a sample of 100, the standard error is 10 divided by the square root of 100, we get 1. So this means that if we take samples of 100, the average difference we can expect by chance is just 1 liter, right? Because we said the sampling distribution is much thinner than the distribution of the population. So what we can expect by chance in this huge sample of 100 participants is just 1 liter. We can expect an average difference of 1 liter in the sampling distribution of n equals 100. Now this will look like this. Okay, so this is our sampling distribution. Okay, actually, not sure that this is correct. Now we have the mu and we have the different values, what we can expect by chance. Now, when we calculate the statistic, we ask how extreme is our result, or in another way, how many standard errors are we above or below the mean? Now, why we ask that? Because the most likely result is exactly on the mean. What does that mean? If artists are not different from the general population, a sample of 100 will usually give us exactly this result. If artists are not different, but if artists are different, we'll get a more extreme result, right? If they're different, we'll get an extreme result, and then we'll say, oh, this result is so extreme. It's unlikely that artists are the same as the general population. So that's the Z statistic, which we talked about before. We get the obtained difference. That's that. The obtained difference, 2, divided by the difference we can expect by chance, 1, basically expressing how many standard errors are we above the mean of H0. And we get 2. So this is our value. Yes, you want to ask.
When I ask for extreme results, I would be a t-score?
The extreme result can be expressed in t-scores or in f-score. It depends on the statistical tests that we're conducting. This will just give them this information. It's a one sample, and we know the sigma in the population. Yeah.
In regards to variability, you're always using by chance as a difference between by chance. Because you're still talking about the HO population. Is that why you're always using that? In the last couple of slides, you're always connecting the average difference between mean. I mean, average difference is based on chance.
Yeah.
You're using that because we're still working with the HO population. Like, well,
Yeah.
is that why? Because it's always by chance in that regard. So we only obviously obtain.
So we're trying to express this distribution, right? So this is differences we can expect by chance. Assuming that H0 is correct, these are all differences we can expect by chance.
Why by chance? Why all by chance? Why all by chance?
If this is true, if H0 is true, then you know that in a sample of 100, then about 2% of them will be 12 meters. But the most of them, many of these samples will be around here.
But it seems to me that like you're saying that we see the like by chance, but until we derive like our final result, like where the H1 distribution lies and where we place our sample mean, essentially it's all by chance. Is that what you're always? No, it's not why you're placing. Always saying like every difference we find here is by chance. That's why I'm confused.
So we're trying to express. Okay, I feel like I lost a little bit. So I'll try to gather you together. We're trying to express the obtained difference in, is it larger or smaller than the difference that we can expect by chance? Okay, so this connects to the sampling distribution. The more extreme the value, the less and less likely we got it by chance. Because the most likely result will be exactly 0 standard errors from the mean. That's the most likely result. Okay, so we got this result, right? Z equal 2. And then we ask, is the result extreme enough? Extreme enough for what? For us to conclude that artists are different. That's what we want to say, that artists are different. If our z-score is, in this case, larger than the critical z-score, then our result is considered extreme and unlikely to occur from the H0 population. In other words, we say a significant result. Right? This is the critical z-score. In a two-tailed test, we get 1.96 and minus 0.96. So we say it's a significant result. Right? This is not QQ, of course, and just trying to fill in with the theoretical explanation. So what does it mean to have a significant result? Okay, first of all, do anyone have any questions about these statements? Yes?
Can you just say the critical value again? It's 1.96 and what?
Minus 1.96. In case of an alpha of 5% and two-tail, these will be the values. Now, we are going to use the t-tables, the critical values tables, but not for a z-score. Okay? The z-score, if we're asking a question about the z-score, we'll just give you the critical value. Okay, so what does it mean? So if our calculated statistic, which represents our sample, is more extreme than the critical value, which represents what is considered to be extreme, then this, follow me closely here, then we say that the likelihood to get such a result by chance is less than 5%. Okay, it's a big sentence to understand. We get it like intuitively. We heard it so many times that we understand it generally, but what does it exactly mean? It means that assuming that this is the distribution of artists, right? Artists are not different from the general population. If we assume that, then getting this result will occur only in less than 5% of the time. This means that if H0 is true and you replicate the study, there's almost no chance that you'll get another extreme result. Right? You replicate it once, you replicate it twice, you replicate it 3 times. Eventually, if H0 is true, you'll find values around here. But we say that it's an unlikely result. An unlikely result, assuming that H0 is correct. And then we say, okay, if it's such an unlikely result, let's say that H0 is probably not correct. Let's reject H0. Guys, asking me something about the theory? Okay, if you want, feel free. Okay, is this idea clear? Quiz level clear? Yeah. Okay. So, one more time. What does it mean to assume that H0 is correct? Right? We always say that, assuming that H0 is correct. If we assume H0 is correct, we say, let's think for a moment that artists are not different from the general population. Okay? Artists are the same. That's our mindset. If artists are the same as the general population, it means that H0 is the sampling distribution of artists, right? When we sample from the general population, we're also sampling from the population of artists. If we're sampling from here, then the most likely result will be exactly in the mean, right? Agree with me? That's the most likely result if this is the distribution we're sampling from. What's an unlikely result? Farther and farther and farther away from the mean, we'll say, oh, that's an unlikely result. And if it's an unlikely result, that is, we compare it to the critical value and it's more extreme, then we say, oh, look, it's unlikely to get this result out of here. It probably didn't come from here. It probably came from a different population. Then we say, okay, so it's not one population. These are two different populations. And the chief finding will be that the likelihood to get this result is less than 5%. Let's see what we have left in the slide. Then the null hypothesis is unlikely, and we reject it. And we reject the null hypothesis. We never accept H1, right? We never say H1 is absolutely correct. We never say that. We never have this kind of confidence. We have some confidence, but never 100%. And in short, just a sec, if Z, in this case, larger, though the accurate description will be more extreme, okay? If Z is larger than the critical Z, then the p-value, the likelihood, is smaller than 5%. Alpha. Yes? Yes?
So if I say that HO is seemingly true,
Yeah.
then the critical value, no, then if the hypothesis is more extreme than the critical value, we say
It's probably not true.
that it's not true.
Probably not true. We never say
So
it's definitely not true. It's probably not true. Right? There's a modesty to statistics. We can never say this is a fact. Right? This is a finding, this is a sample, and it's unlikely that this sample reflects H0. It probably reflects H1. Okay. Any more questions about this rephrasing, rehashing of the same theory? Okay. I'm going to assume that everyone's on board. Yes. So what does it mean that P is smaller than alpha? P represents probabilities to get our sample from this. Right? We want P to be very, very small. We want to say it's an unlikely result to occur from this. Right? And we set the standard. What's an unlikely result? Unlikely result will be 5%. Right? Try to remember the hats we had last week. Shh, guys. Try to remember the hats. We said, okay, we can always draw by chance a blue ball from the red hat. Right? but it's an unlikely result. The more likely result would be taking a blue ball from the table. Right? So if this is an unlikely result, then we say it probably came from a different task, right? A different population that is somewhere around here. So the p-value reflects the probability to get this from this distribution. And if the p-value is small, right, smaller than 5%, we're happy. We say probably not here. Yeah, exactly. Now here's a source of confusion, right? Look at this formulation. If z is larger than z, the critical z, then p is smaller than alpha. Now, if I see this, I don't understand anything, right? Trying to remember this formulation is, some people can do it. I can't do it, okay? If I don't understand what it means, I'm lost. So what I'm asking is, as we said, always translate it. Consider statistics as a foreign language. So you have to understand everything in this sentence. You have to understand what does this Z stand for, right? Z representing our sample. It's an obtained difference versus difference expected by chance, or the value of our sample expressed in standard errors. You have to understand what's the critical Z-score, right? Critical Z-score representing an unlikely result. You have to understand what's the P, what does it stand for, probability. Probability, it's so difficult to wrap your head around it. The likelihood to get this from H0. And then you understand the sentence. Okay, yes? Basically, yes. Alpha is the critical value expressed by chance, like the percentages. But the critical value is the reflection of the alpha in Z-score. In every case. Exactly. Okay. I hope I haven't lost all of you to despair. Okay, let's continue. So I want to stand on an important point. What happens if we have a larger difference if we can expect by chance? So this is the first case, right? This is what we have now. So let's call this case the low variability case. The average difference expected in the population is 10, okay? So the average difference expected in the sample distribution is 1. Yes?
You can say the average and use standard deviation.
Exactly. Average difference. The standard deviation is an average difference. Right? Because variability is differences. Let's take a case of high variability. Now, what we can expect in the population is 20 liters. Right? Some Australians will drink 30 liters, some Australians will drink 50 liters. Okay? So if we have such high variability, the standard error will also be larger, right? Now we have a standard error of 2. And then the average difference here in the sample distribution is larger. And now when we try to express our obtained difference as how many standard errors above the mean, we get just 1. Now 1 is not extreme enough, right? It's the same critical Z-score, right? The variability did not affect the critical score. It's the same critical score. It's the same thing that we say. This is considered extreme enough. It did affect the calculated score. So in this case, it was significant. In this case, it's not significant. Yes?
What makes it extreme that it's over the top?
When it's more, it's beyond this point. When it's beyond that. Okay? So in this case, just because we have larger variability, we say, okay, the same obtained difference is now considered a likely difference. Right? It's likely, it's very likely to get a difference of 2 liters in this case. So whenever you hear there's a difference between this and that, you always have to ask yourself, how big is the difference? Are you expressing this just in averages? Right? The same thing I told you about mental rotation tasks in the first presentation. People hear A is larger than B. And they hear such a big difference, but if we look at variability, we can see, no, it's not such a big difference. Okay, yes?
Once again, how we see variability,
Okay, so here we have a sigma of 20, right? The average difference expected in the population of Australians is 20 liters of alcohol. It's a large difference, right? Much larger than 10. We get this value and try to calculate the standard error, right? The average difference in central distribution. So we get 2. Right? So now the obtained difference of 2 liters that we found, right? We got x minus mu, x bar minus mu. We got 2 liters. Expressed as standard errors, we get just 1. Right? So when we have large variability, this is just 1 standard error, while this was 2 standard errors. Yes?
does that mean like it's one standard deviation going to the mean?
Exactly. Standard deviation in the sampling distribution. But yes, exactly. Right? So the standard error is the standard deviation of the sampling distribution. It's just 1 standard deviation from the mean. 1 is not impressive. 2 is. Okay? It seems a bit arbitrary, right? 1 is not impressive, 2 is impressive. But basically what we want is the largest value as possible. The more extreme the result, the more confident that we found an actual result. Okay. Think about this case. If artists would bring, in Australia, would bring 60 liters of alcohol on average, right? That's such a large obtained difference that in both cases, it would be considered an extreme result. But that's always what we're going to look at. Obtained difference versus difference expected by chance. Okay, moving on. Yes, not moving on.
Sorry, I think one thing is about what you think higher variability.
So here's the conclusion. The difference is considered unlikely, right? This difference is considered unlikely to occur under the null hypothesis only if it overcomes the difference expected by chance. So the larger the difference expected by chance, the less extreme the result is considered. Right? We're trying to overcome what we can expect by chance. We're trying to say, look, this result is not a cause of chance.
This is not my very extreme result.
Exactly.
So is that variability?
What's extreme? Ask yourself, what's an extreme result?
When there's high variability?
When the obtained difference is larger than the difference expected by chance, we say it's an extreme result.
I understand that, I'll go back to
What we expect by chance is variability. Right? Variability, think about it this way. Variability is differences. Right? This is differences that we can expect by chance. The larger the differences we can expect by chance, then
I've been looking at an arrow
this is more difference expected by chance. Let me give you the reverse.
That's better or no? That's good or no?
This is bad for us. Okay? This is bad for us. Let me give you
variability?
Larger the variability, the worse it is.
exactly. Let me give you one more example, and then we'll move on. Okay? Think about a case where, let's say, there's an island of Cyclops. Okay? All the people in the island have just one eye. okay? And then, guys, listen. Let's say we have an island of Cyclops. All the people in the island have just one eye. And then a boat arrives with people who all of them have two eyes. Okay? And then we want to ask ourselves, do the people in the boat have more eyes than the people in the island? Okay? Now, everyone in the island have just one eye. There's no variability at all. In that case, even if the average was, let's say, 90% of them had one eye, and only 10% of them would have two eyes, the conclusion will still be, yes, they're different on average. Okay? Because any result that's more than exactly one eye would be considered an extreme result. If there's no variability, any result reflects a difference. If there's huge variability, we're very uncertain and we're very unwilling to say this is a significant difference. So the larger the difference, the less extreme the result. The smaller the difference expected by chance, the more extreme the result. Yes?
You said before that if it's larger than the difference expected by chance, it's considered an extreme result, but not necessarily extreme enough to reject the null hypothesis.
Right.
Do you still talk about it in terms of extreme?
Right, so we want it to be much larger.
Yeah.
Right?
But you're comfortable saying it's extreme anyway? Or you wouldn't refer to it as
I won't refer to it as extreme. We want this to be much larger, extremely larger, if you will. Okay, so the point here is that we want our samples to have low variability. Remember last week we talked about power, right? And when we said about power, we want low variability. We want homogeneity in our samples. Okay? We want larger samples to have thinner sampling distribution. Okay. Who's worried that they didn't get it enough for the quiz? Not a lot. Okay. Again, trying to reassure you that I think you got it. For the quiz, for the purposes of the quiz, I think you got it.
But
Okay.
definitely doesn't result that we are even learning.
Yeah, exactly. If you didn't see it last week, it would be easier.
No,
Okay. Let's continue. Okay, let's continue. One thing about grades, I don't know if I told you that. I'm not expecting everyone in this room to get 100, right? It's impossible. But I do expect, what I do want as a goal of mine, is that if you imagine what you would generally get in statistics, I would want you to get like 8 to 15 points over them. Okay? So if you close your eyes and imagine, what will I get in statistics? Oh, it's probably 65. I want you to get an 80. Okay? That's my goal in terms of grades. Okay. One sample t-test, very similar to one sample z-test. Only we don't have the standard deviation of the population. So this, I'm going to run through it. Yes?
On our quiz, are you going to tell us when you want us to use a Z or a t-test, or are we going to have to?
You might have a question where you're asked, what is the correct test used? Okay, so don't worry about it. Okay. The French researcher hypothesized that artists in French drink more than the general population in France. One-sided hypothesis. He sampled 100 artists and compared the average score, 14.7, to the known average in the population. Also a true result. French people drink even more than Australian people. Unlike the Australian researcher, he did not have the OECD data and therefore did not know the standard deviation of the population. Okay, so we did not know sigma, so we don't know what the standard error we can calculate. calculate, we have to estimate. If we don't know sigma, we don't know what we can expect by chance. When sigma is unavailable, we will use a close estimate of the standard deviation of sigma based on our sample. Okay, that's the next approximate estimate of the standard deviation. So in terms of do we use a z-test or a t-test, if we know the standard deviation of the population, z-test. If we don't, we use t-test. So how do we estimate? We use the unbiased standard deviation of the sample. You talked about it in the recitation. The unbiased standard deviation of our sample will reflect the closest estimate we got. We calculate the sample standard deviation. We need to follow the same steps we learned in lesson 1, which means sum of square deviations from the mean transformed into variability, transformed. Just a sec. Okay. So just one reminder about the sum of squares just a sec. The sum of squares versus the s squared, right? The variability. We said that the more participants we have, sum of square will what? Will become larger, right? Sum of squares is unstandardized. Look at what we have. Just one observation minus the mean squared. It just becomes larger and larger and larger. On the other hand, variability, s squared will what? Not necessarily smaller, but not larger. Right? The more participants we have, we simply divide by n minus 1. So s squared should not become much larger. Okay? If at all, it shouldn't become larger. If we have a sample of 10 and if we have a sample of 100, s squared shouldn't become larger. Now, you talked about it in the recitation, and it's not part of the quiz, so I'm going to just go over it quickly. N minus 1, right? We divide by n minus 1 and not by n. N will be the biased version, right? We'll get a larger value if we divide by n minus 1. Okay, so we fix the bias that way. But the more participants, the less relevant it is, right? If I have 3 participants, SS divided by 2 versus SS divided by 3 makes a whole lot of difference. If I have 1,000 participants, SS divided by 1,000 versus SS divided by 999, not a big difference. So we say that the larger the sample, the better the estimate of chance. If we could sample 1 million people, the estimate will be very, very close, very, 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 very close to the real sigma in the population. Yes? Not necessarily. This is just us trying to estimate the difference expected by chance. The sampling distribution. Absolutely. Okay, yes. Of the population. Of the sample we always have. We have the actual observations. Okay, so let's say we found that SS equals this number. We get that S squares equal 225. Standard deviation is 15. Okay, so based on our sample, we say that the average difference expected by chance in the population is 15 liters. Okay? And then, of course, we calculate the standard error, and we say the average difference expected in our sampling distribution is 1.5. From this point, we just use the same moves as the z-test, right? We just do the same calculation. We're trying to express the t-score the same way we express the z-score. The t-score is how many standard errors are we above the mean. Or below, but in this case, again, above the mean. Okay, so I just went over this quickly. The main point here is this sentence. When we try to estimate the difference expected by chance, when we have a larger sample, we have a better estimate. I think I'll skip this slide because it's not for the quiz, and I'm thinking that it might be.
Yeah.
Yes. Yeah.
Where's the difference between the test and the test?
So in the z-test, we actually know sigma.
I'm just saying they're very clear.
The,
I mean, the sigma sigma.
right. If we know sigma, we conduct a z-test. If we don't know sigma, we have to go through this long process
Okay.
in order to estimate sigma. Okay, so I'm going to skip this slide, okay? If you want, you can see it in the, it's something that the TAs will also go over with, or already have, I think. Yeah. You can read about it if you want in the presentation itself, it's in the book, but it's not part of today's agenda. And this is just a summary of differences and similarities between T and Z. Again, something that you somewhat know, it's not part of the quiz, so I don't want to delay because we don't have much time. Okay, independent sample t-test. So that's a different kind of test. Okay, one sample versus two samples. The Estonian researcher wondered if artists in her country drink different amounts than non-artists. Okay, so artists versus non-artists. Okay, not the same thing as artists versus the general population. However, she did not have the mean of the population. She sampled 50 artists and 50 non-artists and compared their scores. She found that non-artists drank 8 liters per year, whereas artists drank 14.6 liters per year. The obtained difference. Anyone Estonian here? Okay. Large difference, right? The difference that we found between one sample and the other sample is 7.6 liters. But again, we ask, is the obtained difference larger than the difference expected by chance? Okay. Now, how do we measure the difference expected by chance in this case? When we have two separate groups, we use an independent sample t-test. The standard error is based on the average estimate of chance in both samples. Okay, in both samples. We have to calculate a pooled estimate of chance. Okay, now this is going to be a bit theoretical. I need all your attentions with me. Last slide.
Based on average.
An average estimate of chance from both samples. So, what do we have? Now, I want you to follow closely, okay? This one is a bit tricky. Now, we have the sampling distribution of non-artists, and we have the sampling distribution of artists. Okay? Assuming equal variance, it's the same kind of distribution. Now, what's the most likely result? The most likely result is that we get the average of this and the average of this. Now, if we have these two samples, and we try to express them as difference between the groups, we get this, right? Now, what's an unlikely result? For example, it's unlikely to find these results, right? One extreme result and another extreme result. Now, if you try to express this as difference between the groups, you get this, and then so on and so on and so on. And eventually, you take two samples, you compare them, two samples, compare them, two samples, two samples, two samples, so on and so on and so on, and you'll get this sampling distribution. Okay? Now, the point here is these are sampling distribution of averages. This is a sampling distribution of differences between the groups. Okay? That's the whole point here. It's not a sampling distribution of averages anymore. It's a sampling distribution of the differences between the groups. Okay, so just think about this process. We take two samples, we locate them here. We take two samples, we locate them here, and so on and so on. Difficult? A little bit. Now, the main point here for me is, just a second. The main point here is two things. First of all, the variance here, okay, the distribution here, is based on the distribution of these two. If it's a very thin distribution in the original population, it's going to be a very thin distribution here as well. If it's a very large difference, it's going to be a large difference here. Okay. So the idea is trying to emphasize how this is based on the standard errors of the original ones. Okay, that's yeah.
Is there always going to be more variance in that?
The more variance in these two.
No, is there always?
No. It's just
wrong.
yeah, just. Second thing is in our independent sample t-test, we ask what is the likelihood to get our obtained difference. This, right? We get an obtained difference of difference between the averages from this distribution. Same thing as we did before. Now this is a very unpleasant formula to work with. Okay? I can say that it's not likely that you'll be asked about this in the test. In the homework, you'll probably have to calculate this or even this. Very unpleasant formulas. You don't have to copy them. Really, please don't copy them. You have it in a formula sheet. Yes?
What does it mean by when equal? Both results and equal results?
No, equal samples mean the number of subjects. Yeah, number. This I think you already covered a little bit last year. But very good.
But we haven't understood.
The formulas, they're all different types of formulas. Okay. The DF, the degrees of freedom. Okay, from this we get the calculation. So if we have S squared of 196 for non-artists and 441 for artists, we get this. Now I won't go over this in detail. All the calculations, go over it in detail with the TAs. Just the general idea, we base the standard error in our sampling distribution from both samples. Skip that. And eventually we calculate the statistic, which is exactly the same. The difference between the averages, the obtained difference, expressed as standard errors. But because, now this is the important thing, we got a very large difference. 7.6 is a large difference. But expressed in difference expected by chance of 3.6, not that extreme. Okay, 2.1, not that extreme. It's just enough to be more than the critical value, meaning it is a significant result. Okay, one more test to go and then finish for today. I'll just skim it, okay? I know that you're tired already. Skip that as well. Okay, I'll just say one sentence about this. Now, this is the actual formula of the independent sample t-test. You get M2 minus M1 minus this thing. Right? Now, mu2 minus mu1. Usually, we're just going to ignore it. Okay? And just want to say that the independent sample t-test allows us not just to ask, is there a difference between the samples, but is there a difference that is larger than what we would expect usually, okay? So if I have men and women, and I know that the difference in height is about 5 centimeters, okay? I develop a new drug to make only women taller, okay? I can examine my new drug against this expected difference. That's just all I want to say about this slide. Okay, one last thing for today. Didn't get the last one, I know.
So scared. We're gonna need to use it because I don't get.
We'll always expect the differences here, basically.
No, actually, we have 2 means for the sample and 2 means for the population. Why is M2 minus minus?
So this is if you expect a certain difference. Maybe we'll focus on it next week if we'll have time. Okay, just one thing about the dependent sample t-test. Just to say that again we do the same process. Okay, dependent sample t-test. You know from last year, when do we use it? When we have two groups that are dependent, right? Either before versus after, right? That my result is dependent on my result. Or for example, I have twins, right? Or spouses. So then we use a dependent sample t-test. Now in a dependent sample t-test, we calculate the average difference. The average difference. And we compare it to the difference that is expected by chance. And we do the same process. Now the calculation will be somewhat different, but it's the same process. Okay, enough material for today.